Okay, I guess we can get started. I'm not used to introducing myself. I'm the speaker and the guy who's introducing things. Yeah, I'd like to welcome you to the Russ and Brenda Frank Astronomy Lecture Series, and I'd like to thank them for the support. They've supported this lecture series for over 10 years. We've been bringing in distinguished speakers from all over the place to talk about astrophysics. So, and also send my thoughts out to them. Russ is having some health challenges right now, and thoughts are with him, and he's been a great spokesman for UNLV and understands what we're up to here, knows the programs and the science, so it's really great to have him here supporting our work. And I've also got an email list, so because we do these lectures twice a year, it's great to see such an audience. This is the first one we've done since the pandemic. I mean, hopefully has ended, and or is ending, and it's great to see so many people coming out. And but we have an email list, so if you're interested in hearing about future lectures, I'm just a journeyman scientist who works in the building, and usually we have very distinguished speakers, but one of our guys canceled, and so I had this talk ready to go, so I said, well, let's get going and get on with it. I have a good story to tell, but I'm not quite of the caliber. We have a guy from the Ice Cube experiment, which is a neutrino telescope at the South Pole. He's going to come and talk to us next February, so stay tuned for that. He's a really distinguished scientist, and we have people here working on these things. We have a fantastic collection of astronomers here at UNLV as well. So I think that's roughly speaking my introduction. So I want to talk about, cosmology century. And I'm sorry if you're expecting colored slides. I get a bit burnt out on slides and PowerPoint, so I'm just going to tell you a story. Hopefully the story will capture you. The images are there. You know, JWST has produced astonishing images, and you can find them on the internet, and I could put them up and get oohs and ahs, but I want to tell you a story. So, and it's the story of the discovery of the Big Bang. I want to start by talking about time at the beginning, because I think time, we're not used to the time spans that we deal with in cosmology, which are billions of years. It's hard to imagine what that means, so I'll try and zero in with that. Then I'll tell you basically the last 100 years of cosmology, which have been absolutely an astonishing, I would say, series of success of physical science. And I don't only want to tell it to you as just like a story, like history, well, this happened and then that happened, just a sequence of events, but maybe speculate a bit about why cosmology was so successful. And I want to contrast it. I have another interest, some of my colleagues know, which is water and the supply of water in the Colorado River. And you might say, well, what's that got to do with cosmology? Well, really nothing, but it's the same time period. So 100 years ago next week, November 24th, 1922, the same time that Slipher was measuring redshifts at Lowell Observatory, they signed the Colorado River Compact. Some of you might have heard of that, and set the stage for what I would say is a disaster that we're kind of seeing unfolding right now. Why did that go so wrong? And why was cosmology so successful? I don't know the answer, but I have some ideas. So I'm not trying to blindside you with a talk about water tonight. This is a talk about cosmology, but I want you to keep in mind, you know, just as I go through this story, why was it so successful with our astrophysics, which should be much, much harder than water management? And it's been such a triumph that I would say we know more, with more certainty, what happened 1/1,000,000th of a second after the Big Bang than we know about, say, human diet or cancer screenings, or we're not quite sure. We keep getting different information. But we know a lot about what happened in the first 3 minutes of the Big Bang. So let me think about time for a minute. And so the Earth is 45 million centuries old. And that's comparable to the number of seconds in a year, roughly speaking. So if our life, you know, we live 80, 90 years if we're lucky, the amount of time that we spend on Earth, comparable to how long Earth has existed, is the same in proportion as 1 second compared to a calendar year. So a lot of seconds have gone by, you know, a lot of centuries have gone by. Okay, but this century is different to all of the other centuries. It's unique of the 45 million centuries that have come before, for two reasons from my angle. You can have your own reasons, but one, it's the first time that we as a species on Earth is determining the fate of all of the others. That's never happened before. where one species is causing, extinctions and changing the environment so quickly that we're having a very high extinction rate, and that's never happened before in the history of the Earth. And also it's the first, like I say, cosmology century, that's the other unique aspect, where we've actually understood something about the origin and evolution of the universe and turned it into hard science as opposed to wild speculation. And so that's one way to look at time. Well, a lot of time has elapsed since the formation of the Earth, but the Earth is billions of years old. I found another way for a lay audience maybe of relating timescales is to think of, instead of using our calendar years to do time, think of a galactic year, which is how long it takes the solar system to orbit the Milky Way. And in those units, the Earth is roughly my age, it's 60 years old. And I mean, the universe is 60 years old, and the Earth is about 20 years old. So the Earth appeared when the universe was 40 years old. It's been there, for about a third of the time. And with the James Webb Space Telescope, we're looking back to, on this 60-year time scale, taking pictures of galaxies as they were when the universe was 2 years old. So it's kind of amazing how far back in time we can push with these amazing telescopes. And the stars in those galaxies were born when the universe was only 1 year old. So we're pushing back towards what we call the cosmic dawn, the birth of the first stars and galaxies. No longer just a subject of speculation, of daydreaming and, but actually measuring, seeing the universe switch on with the first stars and galaxies. And so how did we get to this point of, being so advanced really in our understanding of the universe over the past 100 years? And my story I'll start it about 100 years ago, a little more, when Einstein was developing his general theory of relativity. This isn't a lecture about that, but he did a new theory of gravitation that sort of included Newton's theory but improved on it. And with his theory of general relativity explaining motions of the planets as things trying to move in straight lines in a curved space-time, whatever that means, I'm not going to really go into detail here, but he could explain what was known about the motions of planets in the solar system. This was from 1910 to 1920 he was doing this work. And he could explain something maybe a little bit extra, which was the anomaly in the orbit of the planet Mercury. So that was very good. But one of the things with science, with the physical sciences, is we like to make predictions of things that were not known at the time the theory was developed. And so Einstein imagined a test of his theory, an experiment whose results were not known at the time. And the experiment he conceived was to take a picture of the sky surrounding the sun during a solar eclipse, when it's dark enough during the day, because the moon comes in front of the sun, that you can see the positions of the stars near the sun. And Einstein predicted that the stars would all be displaced slightly from the sun, from where they would be if the sun hadn't been there. How would you know that? Well, you could take a picture a few months earlier or later when the sun wasn't in the way and compare a picture with the sun there, but during an eclipse when you could see the stars. And Einstein predicted the displacement, the amount of the displacement of the stars. He tried to do it in 1917. He went to Russia. He was nuts, like all scientists are, in the middle of, German national wandering around Russia with scientific equipment. Luckily for us, he wasn't shot. He was sent home. They found him and sent him home and believed his story that he was just a scientist and not a spy. And the real experiment was conducted by two British scientists, a very famous astrophysicist called Arthur Eddington and another guy called J.E. Dyson. And they went off to the southern hemisphere, the South Atlantic, west coast of Africa, and the east coast of Brazil to Sobral. And they took relatively primitive equipment for, compared to what we use today, and took pictures during this solar eclipse. And as usual, there were difficulties. It was partly cloudy. The equipment, the photographic plates expand, and so they'd act differently during the day to night. You had to compare all this. But the fun thing with science is they published their results, and the results are still, you can Google them, you can find the original article from 1919. We have a record of all this stuff. And just for fun, during the pandemic with one of our students, I reanalyzed the data, because they gave the numbers. Said, here are the positions of the stars, and you could sort of compare their analysis just to see what the story was. And this, our friend Mario Livio has told this story right here, actually, a few years ago, from his book, Brilliant Blunders. But the measurements were not as conclusive as has been made out. I would say, yes, if you're a betting person, I would have bet on general relativity based on those results, but it wasn't a slam dunk like an absolute guarantee. Some of the data actually supported Newton's measurements, surprisingly, but they weren't as good quality. So science is a bit subtle sometimes, not so much in the New York Times, which published a headline, "Lights all askew in the heavens," and explained that a new genius had arrived in the world, and correctly, and that Einstein's name has been mentioned in the New York Times every year since then. So, and he's sort of regularly mentioned in Nobel Prizes now associated with, gravitational waves and various things in astronomy. So it was a great triumph of his theory, the idea that you could make predictions, but really it wasn't until the 1960s that very precise measurements, much better quality measurements, enabled us to confirm Einstein's general theory of relativity. So just to say, astronomy is a bit, when you're on the frontiers of knowledge, it's not immediately clear what direction to go in. But Einstein was confident, and he believed enough in his theory that 2 years earlier, he tried to apply his theory of general relativity to the whole universe. He said, well, I have these equations that describe how mass behaves, and what do they tell us about the universe? And he did something seemingly odd. He did a model of the universe of uniform density. It had just the same density everywhere. Well, that was known to be false at the time, because what we knew from observations was there was a Milky Way, and then nothing, empty space beyond the Milky Way. That's all that was known in 1917 when he published arguably the first paper on cosmology as part of this story. And so why would he do that? Well, he wasn't really interested in cosmology because it didn't exist. The Big Bang Theory didn't exist. What he was interested in the problem of inertia. So we have a hockey team here, I'm informed, and they're doing very well. And when they hit the hockey puck, it keeps going in a straight line until something happens. So that's called inertia. Things want to keep moving in a straight line. But no one knew why. And so Einstein, who was a fan of Ernst Mach, who was another physicist, Mach number, you might have heard of that guy. Mach was interested in the problem of inertia and had the idea that the property of inertia, this mysterious tendency for things to keep moving once you get them moving in a straight line, that it was caused by the interaction of a mass with everything else in the universe. And so Einstein thought, well, let's apply that idea to using general relativity. And let's just assume a universe uniformly filled with matter and unchanging in time. And to his surprise, he found that was impossible. You couldn't have a universe not changing in time. His equations of general relativity predicted an expanding universe or contracting, but it couldn't stay suspended as it was any more than this bottle could sit here if I let it go. So that was a sort of shock to him. And he said, well, he did sort of the reasonable thing. He said, well, we know the universe is not expanding because 1917 there was no evidence of that. And so he said, therefore my equations must be wrong. I have to modify my equations of general relativity to stop this horrible expansion of the universe that is not true. And he invented a thing called the cosmological constant, a sort of anti-gravity, where you can imagine the force of gravity pulling this thing down, and then but it hangs in midair. So you say, well, there must be an upward force fighting gravity. That was the cosmological constant. And that enabled his universe to sit there unchanging in time, which is what he wanted. Unbeknownst to him, when I was a kid, I liked to read the Winnie the Pooh stories, and you're like, well, what's that got to do with anything? But the guy who wrote those was an astrophysicist, a cosmologist, and a few years later, he showed that universe with a cosmological constant was unstable. If you added an atom to it, it would collapse. If you took an atom away, it would start expanding. So Einstein, even though his universe that he'd created with this cosmological constant was a bit of a pipe dream. It was like, well, it kind of worked, but if you just tweaked it, it would collapse, it wouldn't. So that was kind of an interesting thing. But anyway, unbeknownst to Einstein at the time, astronomers were busy with their telescopes, just making measurements. And one of the mysterious things with the telescopes was these objects called nebulae that had been discovered in photographic plates. They were sort of, as the name implies, cloudy patches of light. And no one really knew what they were. And so could they be just faint objects very close by? or extremely bright objects very far away. No one had any idea. And so we have a world expert on gamma ray bursts. When I was in the 90s, people were thinking about these things. There were the same debates, whether gamma ray bursts very faint objects in the solar system or whether extremely distant objects. No one knew. And there was a guy called Slipher at Lowell Observatory, not very far from here in Flagstaff. If you go to Flagstaff, Lowell Observatory is still there. You can still see the telescopes. Maybe more famous for the discovery of Pluto by Clyde Tombaugh, 1931. But Slipher was making these measurements of the nebulae, very difficult measurements, to using a sort of prism type thing to spread out the light from the nebulae, and you could measure how fast they were moving. And so he discovered, by 1922, he'd measured about 44 of these objects, and 90% of them were moving away from us very, very fast. So that was something interesting. By very, very fast, I mean thousands of miles a second. And so much faster than the stars in our Milky Way. So that was kind of mysterious. There were these cloudy patches of light that were just flying away from us. What could they be? And now a name you will surely have heard of is Hubble came into the picture, of Hubble Space Telescope fame. And he was working at Mount Wilson in the other direction in California. And he was trying to look at stars in these nebulae to see if he could measure their distances. And by 1926, he had some rough distances to the nebulae. And so then enters another guy in this story, a Jesuit priest, Georges Lemaitre, working at the Catholic University of Louvain, and he combined Hubble's distance measurements with the speed, the velocity measurements of Slipher for these mysterious nebulae. And first of all, the Hubble measurements showed that the nebulae had to be very far away, so far away that they were Milky Way type objects, galaxies as we now know them, but they appeared small on the sky because they were very far away. So Hubble was computing very large distances for the nebulae. This guy, Georges Lemaitre, combined the two measurements and found the first indication of what we somewhat unfairly call Hubble's law, that the nebulae that were further away were moving away faster, and the nebulae that were closer by were moving away slower. And there was sort of two ways of interpreting that. One was to say, well, there's just been a giant explosion, that it's just flung everything away from the Earth, and the nebulae that are moving faster, as in an explosion, something gets a faster initial speed, it'll go further in a given time. If you take a picture at a given moment, the ones that are moving slower wouldn't have gone as far. But Lemaitre was familiar with the work with Einstein and these cosmology ideas and said, no, the correct interpretation is the general relativity idea, that we live in an expanding universe. So that was sort of the first pillar or piece of evidence for the Big Bang that emerged in 1927. Hubble has telescopes named after him, and he's super famous. Lemaitre, not so much, but because he published in French. So if you want to get on ESPN in science, don't publish in French in a Belgian obscure journal. So nevertheless, there's a bit of a sort of detective story that Mario told a few years ago, but the paper was republished in the monthly notices of Royal Astronomical Society, and Lemaitre left out the key bit about the Hubble law, so that was another mistake. He should have left it in there. I'm not sure why he did it, but Mario found out that he had done it. People had thought there was some sort of cloak and dagger stuff with going on to discredit him, but that was not the case. But anyway, I don't know, I'm not too worried about credit myself. But anyway, that's part of that story. So in 1929, Hubble published the same thing in English with a much bigger audience, and so it became known as Hubble's law. And that was the first piece of evidence for the expansion for the universe. I like to think of the Big Bang, since Lemaitre was a Jesuit priest, a little bit as a cathedral, even though a cathedral is a religious building, and I'm not religious, and science is independent of religion. Why would I say that? But Martin Rees, who I admire so much, I love to read his writings, he says, in the Middle Ages, when they built these cathedrals, the people who started building them knew that they would not be alive when they were finished. They had faith that these buildings would take so long to put up, but they would last so long that it was worth embarking on this work that would remain. It was a long-term thing and built to stand the test of time. And so that's where my analogy with the Big Bang is. I think this Big Bang theory was built to withstand the test of time. The guys who started it are all gone. You know, all the names I can think of, you know, Lemaitre and Hubble, Friedman, I don't know, Einstein, anyway, all of these names, but the edifice still stands. They didn't see its completion, and so I think there is that element in science of cathedrals. We build things that are built to withstand the tests of time. And another analogy that pops in my head, because I'm obsessed with rivers, is for the Big Bang, you can think of the mainstream of science as a river, since I've run a lot of rivers in my life. And then when you're running a river, actually one river many times more precisely, but for the Colorado River, you can see the main stem, and then when you're there, you look to your left and your right, and there are tributaries. There are sort of side canyons, but not all of these side canyons are going to go anywhere. Some of them lead to something, end up in the mainstream, and some of them just peter out. And that's sort of the craft of the scientist, is sort of smelling which are the good problems that are going to keep going and contribute to the mainstream of knowledge, and which ones are going to fizzle out. And that wasn't clear at the time. So I'm going a little bit back and forth in time. And so now we've established, the universe is expanding. It's consistent with Einstein's original idea. Incidentally, worth noting, the way we proceed in science is Einstein then said, okay, we don't need this cosmological constant. He made an adjustment. He said, I'd put it in there to stop the universe expanding, but the universe is expanding, so we modify our ideas. That's sort of rational behavior, which we don't always see in other fields of endeavor. So it's worth noting, Einstein wasn't just said, well, this is my constant, I don't care what nature said. He said, no, nature said no. This constant in that form, designed to stop the universe expanding or collapsing, was no longer needed, so they did away with it. Now I have to backtrack a little bit. I've taken you to 1929. Backtrack to 1920, where the same Eddington who did the eclipse expedition was wondering about why the stars shine. That was another mystery, just fundamental mysteries. What was the source of energy for the sun? The geologists had pointed out that from the age of the rocks on Earth and evidence of life, that life had been around for a long time on Earth. Life without the sun was not imaginable. Therefore, the sun had been around for a long time. But what source of energy could it be? Chemical energy didn't work, the sun contracting, none of that worked. So Eddington suggested that from the previous theory of Einstein, the special theory of relativity, the most famous equation in physics, E equals mc squared, that the constituents of atoms weighed less, or rather more, than the atoms themselves. So his idea was, at the time, the helium nucleus, so the periodic table of the elements there, the next element up from hydrogen was thought to consist of 4 protons. You might say, well, what about the neutron? Well, the neutron hadn't been invented in 1920, or discovered rather, it wasn't invented. So they didn't know about that. So they thought helium was 4 protons. So the question was, how could you stick 4 protons together to make a helium nucleus? And the intuition would be one at a time. You just stick 2 protons together, add a 3rd proton, obviously, and then a 4th. Except there was nothing in nature, no stable configuration of 2 protons. The 2 protons had to hang around long enough together for a 3rd one to join them and stick to them. And so that was a problem of the details of how to make it happen. But indeed, the helium nucleus weighs less than the 4 protons. So if you stuck 4 protons together, you could, by the difference in mass, release energy, and there was enough energy potentially to power the sun. And so, but it didn't work. There was no mechanism. So now into 1934, a guy called Hans Bethe came up with this idea that maybe you could do it by just adding protons to a carbon nucleus. And so one at a time. The carbon nucleus exists, it's stable, okay, why not? Add 4 protons to a carbon nucleus, turn it into oxygen, then the oxygen would spit out a helium nucleus. Net result, you got what you wanted. You've made what the alchemists dream, helium out of hydrogen. You've turned one chemical element into another and released energy. Of course, in the Alice in Wonderland sort of logic, but how did the carbon get there? In order to make carbon, you need helium. In order to make helium, you get carbon. You're kind of stuck at that point. What do you do then? You got a problem. So fast forward to 1937, I'll accelerate, so this lecture won't go on forever, but in 1937, von Weizsäcker thinks, well, the universe is expanding, so how about going back in time? Back in time, the universe was denser and denser and denser, as if the walls of the room were shrinking. You'd all end up sitting closer and closer to each other. Density goes up if you go into the past. Might it not have been possible that the carbon could have been formed early on in the Big Bang? And so people started investigating nuclear fusion reactions early on in the Big Bang. And a guy who did a lot of work on this and got justifiable credit was George Gamow and his collaborators. And I'm going to recommend a couple of books in this talk. And one of them is called The First 3 Minutes by Steven Weinberg. It was published in 1973. And I think it's a great description of the process, our modern vision of how hydrogen is turned into helium in the early universe, and what Gamow found. So if you're interested in that, I'd recommend reading that book. It's an old book, but it's a really well-written book if you want to hear some of the real physics of how this works. And so The First 3 Minutes is one of my recommendations. So these ideas were floating around in 1937, but it was really only until 1948 that Gamow came up with his theory of how you turn hydrogen into helium in the Big Bang. Turned out carbon was a moot point. Everything would stop after helium. There wasn't enough time. The universe is expanding very quickly. It's cooling off very quickly. You've only got a finite amount of time, the 3 minutes. It's even less than that. But Weinberg thought he wouldn't sell a lot of books if he called it the first 2 3/4 minutes. He thought 3 minutes sounded better. And so, at any rate, he sold a lot of books, so that's good. And it's a good book. So, but there wasn't a lot of time, and things fizzled out after 3 minutes. And so, but why did it take 10 years to figure it out? And I only found that out last week. I don't know, history kind of entertains me. And it was a lot of the work was done by the military, because obviously they were developing atomic weapons, and they didn't want to publish all the details of atomic reactions. And so in 1946, they declassified all that. Gamow was a refugee from Stalin's Russia. He'd sort of snuck away, allegedly going to a meeting, and then disappeared and went to America. But he only had access to the data when they were declassified, and then he could make his theory. And again, with this emphasis on prediction, Gamow makes 2 predictions of if this happened, and it sounds like, well, this happened in Australia or in, very far, it happened in this room. He's talking about what happened in this room 14 billion years ago. So it's not far away, it's what happened right here, and here and everywhere else. And so Gamow develops this hot Big Bang. The Russian counterparts were not aware of the existence of helium in the universe, so they were actually trying to prevent the formation of a helium. So Zeldovich and those guys were doing a cold Big Bang, because they didn't want, the physics was the same, but they didn't want to form all this helium that Gamow was forming in the hot Big Bang. Gamow predicted the existence of 2 fossils. Fossils are things that we can see today in the spirit of geology, but left over from a long time ago. The 2 fossils he predicts, one is very simple to say in words. He predicted that 10% of the atoms in the universe would be helium atoms. And so that came out of his theory of if the Big Bang was hot, it was high temperatures and densities, the conditions were right enough for nuclear fusion, you would expect 10% of the atoms in the universe to be helium atoms. And the second prediction he made was that there would be, to state it poetically, an afterglow of creation. Or more, as we physicists say, the cosmic background radiation is what my colleagues would know it as. But afterglow of creation is kind of poetic. It's a very faint background of microwaves that would bathe the universe, just this light traveling through the universe left over from the hot Big Bang. 2 predictions that Gamow made. Gamow and his collaborators, Alpher and Herman. And 1950s, moving now through this cosmology century, the abundance of helium, as we say, the relative amounts of helium to hydrogen atoms, almost all of the hydrogen, the universe is hydrogen, with 10% of atoms being helium and 2% being everything we know and love. We have some world experts on planets and stuff up there in the back row. They can tell you why the abundance of elements on Earth is so different to the abundance of elements out there in space in most of the universe. Because you might have noticed it's not mostly hydrogen and helium in this room, but when you look at gas clouds and galaxies, it is. And that was confirmed in the 1950s. I'm an old guy now, obviously, but I still feel like a 7-year-old, like a little kid discovering science, and I'm surprised that I've met some of the people who did this work. And I worked for a summer at Kitt Peak with a guy called Tom Kinman, and in researching this lecture, I discovered that he was one of the guys who had actually made the measurements of the helium atoms, the relative amounts of helium and hydrogen atoms, we were working on a different thing with him, and I didn't realize he'd done that. But that was kind of neat to know. So that's the 1950s. Then in the 1960s, there was a group at Princeton, the Gravity Research Group, that was exploring gravitation. Interestingly, they were funded by the military, kind of an odd thing that the Air Force would be funding cosmology. But I think they wanted more scientists in those days, and they figured out if you gave money to good scientists, they would train other scientists, and then maybe some of them would help out the military or something. But at any rate, they were trying to detect the second fossil that Gamow had predicted, this background radiation, sort of radio waves, slightly shorter wavelengths, that were a faint sort of glow of radiation out there in the universe. So, and science being what it is, there was another group, unbeknownst to them, also in Princeton, that were studying radio waves from the Milky Way. So they weren't even aware of cosmology. They were just studying this. And they found there was something wrong with their telescope. The telescope had this sort of hiss, this kind of noise that they couldn't get rid of. And at first they thought it was the electronics. They were working at Bell Labs. And they thought, well, there's something wrong with the electronics in the telescope. It's just hissing. No, the electronics were fine. Well, the Earth emits radio waves. Maybe there was radio emission from the Earth. They hadn't shielded the telescope properly. No. Maybe there was a radio station emitting. They basically thought of every possible thing that could be running interference. And they couldn't think of anything, so they said, okay, well, this is real. And so they published it, but they had no idea what it was. And a guy from MIT called Bernie Berg heard about this, and he told the Princeton guys, you guys might want to check this out, because these guys at Bell Labs have discovered something that seems awfully similar to what you guys are looking for. And so they went and visited Bell Labs. It was Wilkinson and Dickey. And they were like, wow, these guys know what they're doing. You know, the equipment, everything looks legit. And so Dickey went back to Princeton and said, boys, unfortunately it was all men in these days, almost all men, boys, we've been scooped. Luckily that's changing in science and also in astronomy. And he was right. And so they published in the Astrophysical Journal, the Princeton group, the Bell Lab guys published their finding, and the Princeton group with Peebles et al. Said what they thought this was, what they thought this meant. And the Bell Labs guys got the Nobel Prize for this discovery of the second fossil from the Big Bang. So now the cathedral, as I'm sort of calling it, of the Big Bang, the edifice had these sort of three pillars supporting the idea, right? One was the expansion of the universe, predicted by Einstein's general relativity. A homogeneous universe, uniformly filled with matter, will expand. And the helium atoms, 10% of the atoms in the universe are helium atoms. And then there's this background radiation that's bathing the whole universe that was predicted by Gamow. And so again, the emphasis on prediction, adjusting your ideas, and so on. So that was really putting the Big Bang on a better basis, you know, on observations, not just wild speculation by scientists. And now we change tack a little bit, moving into the 70s, where the idea of dark matter, for historical accuracy, it had already been sort of mentioned by a very prescient scientist called Zwicky in the 1930s, but it really came to the fore in the 1970s was the advent of radio telescopes and detectors in the optical, where you could not only see that these galaxies were moving away, but also see that they were spinning. So, and the analogy might be of a frisbee. You kind of throw a frisbee and it's moving away from you, but it's also spinning at the same time. My scientist colleagues will say, well, that's not the way galaxies rotate, but close enough. They don't rotate as a solid body, but okay. General idea, the spinning. And why this was of interest is because you could use the spin of galaxies to measure their mass. If you know the distance from the center of rotation and how fast something is moving, you can measure the mass interior to the orbit. And so you could essentially weigh galaxies. You could know how much matter they had inside them. And their surprising discovery was made is that most of the matter in galaxies was invisible. It was called missing mass at the time, but the mass wasn't missing. It was the light. So that was a big discovery. That set the stage for the next discovery. And Vera Rubin was a lady who did, a scientist who did that discovery at the Carnegie Institution in Washington, together with Kent Ford, and also the guys in Holland were using radio telescopes where you could go even further away from the center of galaxies and weigh them. Excuse me. So the next thing when you discover these phenomena in the 1980s was the beginning of the age of surveys, of trying to do a census of the universe, to take like a gigantic cube, maybe 100 million light years across, and weigh the universe and find out what's in there. And I had another shocking result. So when they weighed the universe, counting all the galaxies and knowing the mass of the galaxies, adding it all up, you could get the density of the universe, how much matter there was per centimeter cubed in a large region of the universe. And what they found there is the density was surprisingly high. By surprising, I mean the detailed calculations of Gamows' theory of the first 3 minutes put an upper limit, a maximum, on the density of atoms from the periodic table. There could only be so much mass in atoms. And when you did these surveys, the mass, the density of the universe was about 6 to 10 times higher. So now not only was the matter invisible, but we didn't know what it was. It wasn't ordinary atoms. It wasn't iPhones or, well, they hadn't been invented, but pens or pieces of paper or rocks. It couldn't be that, because those things are made of atoms. The dark matter in the universe, following these early estimates of the density, had to be something else. And they were a little bit stuck. So I see young people here. If you want to do an experiment and get famous, detect dark matter. I think there's a Nobel Prize in it for you. I'm not guaranteeing you'll succeed, but that's definitely, I would say, maybe an embarrassment to astrophysics that we haven't detected what we think most of the universe is made of. So the evidence is circumstantial. We have evidence from the rotation of galaxies, from adding up the mass, but we haven't actually built a detector that can measure directly these dark matter particles, although we have a good idea of what we think how they would behave, but we haven't found them yet. So that's sort of the general story of cosmology. I would say in a nutshell, the last 20 to 30 years, and here I'll mention another book, has been measuring the parameters of the universe. Parameters just means numbers. So now we believe in the Big Bang, we think it's real, but we have numbers that characterize the universe. Maybe the density of the universe, the density of ordinary atoms, the relative amount of hydrogen and helium in the universe, this cosmological constant of Einstein. These are all numbers, 4 numbers. The Hubble constant, measuring how fast the universe is expanding, and the age of the universe. 6 numbers. There's a book called Just 6 Numbers by the aforementioned Martin Rees, which tells that story of how we calculate these numbers. And a huge amount of effort has been expended into measuring these numbers. Maybe as a layman, I might be tempted to say, well, who cares? We know the universe is 14 billion years old. Why have a collaboration of 200 scientists to refine that number to 13.78? What difference does it make? We know it's 14 billion. That's good enough. I went to my Astro talk. I'm going to go home and watch Netflix, get on with my life. Why are we making so much effort to measure these numbers to higher precision and accuracy? It seems a bit absurd. We've solved the problem. We know there's a Big Bang. And let me give you an analogy as to why so much effort was made. At the turn of the century, people believed that light traveled at finite speed. But you can't see that. You go home and you switch on the light, and there's no light, and then there's light. You switch on your light beams of your car lights, and you don't see a sort of beam of light traveling through space. You have no evidence, actually, of anything that I've told you. If you go out into the parking lot and say, well, that was a cool story, let me look around me and see any evidence of what this guy's told me, it might as well be Alice in Wonderland. There's nothing you can see with your eyes in the parking lot that supports anything I've told you tonight. So I'm not trying to discredit myself, I'm just trying to say those are the facts. And the same is true of the speed of light. You can't see it. You can't see the speed of light. So why do we believe that light travels at finite speed? Well, we do experiments. So you can measure the moons of Jupiter. The moons of Jupiter orbit Jupiter, obviously, and they're like a clock. They orbit with regularity. But the clock sometimes runs fast. Sometimes it runs slow. Why? Because the distance between Jupiter and Earth varies, and if light travels at finite speed, sometimes Jupiter's a bit closer and the moons appear a bit earlier than expected from behind Jupiter. Sometimes it's further away, they appear a bit later. So that's a piece of evidence for the speed of light. But what if we calculated it wrong? Maybe there's hidden moons, dark matter moons of Jupiter, something's perturbing them that we don't know. So we have an estimate of the speed of light. Now we do another estimate. Let's say we look at a laboratory measurement. So Maxwell's theory of electricity and magnetism, there are two constants that you can measure in the laboratory, no telescopes. You don't need any windows in your laboratory. You can do this here downstairs. Completely different experiment to Jupiter's moons, the experiment done with telescopes. These two independent, so you measure these two constants of nature, combine them, and that gives you the speed of light. Now, if light didn't travel at finite speed, if the whole thing was nonsense, it would be a really strange coincidence if these two independent experiments, completely unrelated, gave the same answer. That's what gives us the confidence that we're measuring something real in nature and not just playing around with equations with algebra. That we get the same answers from completely, and now you can think of 6 experiments, I don't want to go on for hours, but it's the logic of the situation. And the same applies to cosmology, is you do these experiments to try and measure these 6 constants in different ways, some using the background light, the afterglow of creation that Gamow predicted, some using nearby galaxies. We can measure the Hubble constant in different ways and get the same answer. It's not just an artifact of equations. It would be a really odd conspiracy of nature if measuring these numbers in different ways gave you the same answer. I think that's one reason such a strong effort has been made to really measure the 6 numbers of the universe with more precision, independently, using methods that don't overlap. And so I think that's one of the reasons cosmology has been so successful. And so, sort of drawing to the end of this talk, there's a book that Peebles, I can't remember the title, but he published it this year. So Jim Peebles is Nobel Prize winner of 2018, I think. And he published this book, and I forget what the title is, but it's basically the history of the Big Bang that inspired this talk. If you want to delve deeper into these matters, he's a good guy to read. And he's interested, something that I don't talk about much with scientists, but I've always been fascinated by, which is also the methods of science. What is it about science that makes it so successful? This 100 years of the Big Bang has gone from wild speculation of Einstein based on nothing, a theory that he cooked up that wasn't really confirmed by anything, sort of vaguely confirmed in 1919. And he sort of dreamt up this expanding universe, but it was really a backwater of science. No one much was paying attention to really mainstream, well-established science, a really march of success of really understanding the origin and history of the universe. Why did this work? Why was it so successful? It's different when you read it in a book. I've seen it for myself when you've been in the game for 40 years. You witness these developments, and it's been kind of astonishing. And Peebles comes up with these working assumptions of what scientists think they're doing. So I'm being careful in my language. It's not a religion like the 10 Commandments or something. You have to do this, and then you're in the religion. If you don't do this, you're not in the religion. It's an idea that maybe most scientists, and I look forward to feedback from my colleagues, most scientists might agree that's what we think we're doing as scientists. And so I'll give you these 4 assumptions, and I think that's part of the reason that physical cosmology has been so successful, because we tried to follow these ground rules, even though you don't have to, and it's not even clear that those are the rules, but I think that's part of the key to success. I'm being cautious because we're sort of in the realm of philosophy, and it's very dangerous in philosophy to have dogma and so on. But working assumptions. So nature operates by our laws of logic and mathematics expressed as approximations in our physical theories. This is a bit of a mouthful, this statement, but it's very important, key to the success, to understand that what we're doing are approximations. We're not finding the absolute truth. We're sort of hunting around trying to feel our way with experiments and getting closer to the truth, but it's not, and I'll show you why this is important in the final part of this talk. I'm almost there. And so that's the first one. We use the laws of mathematics and physics, logic and mathematics, expressed as approximations in our theories. Then theories worth close attention are good enough approximations to reality that their predictions, they yield successful predictions in applications beyond the situations used for their construction, beyond the evidence used for their construction. That again is a bit of a mouthful. But the point is you have a theory with evidence that was available at the time. Examples are good. I gave you the example of the solar eclipse. That wasn't known when he did his theory of relativity. He said, I'm proposing an experiment to measure something that was not known at the time. So theory's worth, and if you can predict successfully the outcome of an experiment, again, notice the lack of dogma. All it says is, it's worth investigating a little more, maybe. You know, you might be on the right track, maybe not. But it's worth looking more carefully at theories that can predict the outcome of experiments. Another thing that's of interest. Then false predictions, the third one, false predictions force adjustments of theories or the creation of new ones, some of which will be found to be improvements by the tests of experiments. And so you make adjustments. False predictions force adjustments. If you predict something wrong, you say, okay, I predict that the universe is not expanding because I have a cosmological constant. That was wrong. You make an adjustment. You ditch the cosmological constant. You have this constant dialogue with data. Kind of obvious. So, you know, maybe, but I'll show you at the end why I'm saying this. Then the final idea is the iterative improvements of theories driven by empirical evidence will converge on a unique end, the nature of reality. That's another important statement. We're not going round in circles, in other words, just like fashion, you know, like you might wear clothes a certain style in the 1960s, and then you go back to that. So, you know, 2,000 years ago, the Greeks said everything moved in circular motion around the Earth that was at rest at the center of the universe. The Big Bang isn't a fashion. We're not going to be teaching the Greek version of reality in, you know, 20 years that we're just bouncing around. We're converging, getting closer to the nature of reality. So, you know, why indulge in this sort of philosophical thing? What's of interest to me with my other interest in water is what happens when you don't do that? That's what interests me. So I didn't give you these rules just to give you rules just for fun. So now let's look at the same period of time. 100 years ago next week, 1922, the Colorado River Compact was written. Nature operates by our laws of logic and mathematics, expressed as approximations in our physical theories, not in the management of water. Nature operates by laws written in documents by lawyers, independent of physical theories, independent of nature. That's the exact opposite of what was the success of the Big Bang. We decided that the Colorado River goes at 18 million acre-feet a year on average. It's a law, end of story. So this is, I think, a really important idea. It's obvious maybe, but to keep in mind. And that's one of the reasons everything went off the rails, is it wasn't true at the time, it was never true, you know. So theories worth close attention are good enough approximations to reality that they make successful predictions. The 18 million acre-feet a year assumption was sort of a prediction. It said, you know, 1920, that's what we believe. In 1930, 40, that never happened. There never was 18 million acre-feet a year. If you look at the average for the 20th century, 15 million acre-feet a year. If you look at this century, 12 million acre-feet a year. Acre-feet a year is a measure of the volume of water that nature delivers down the pike. But the number in the compact 100 years later is unchanged. Nobody modified anything. It was frozen in there. And that's why that water management has been a disaster. It was the opposite of science, where you accept that your knowledge is an approximation and you adjust it as new information becomes available. So false prediction force adjustments of theories. No, the prediction was false, but no adjustment was made. Again, 100 years later, 18 million acre-feet is what the Colorado River delivers. Never mind that it's actually delivering 12. And finally, the iterative improvements. If you keep doing this, you'll get closer to the nature of reality. Well, that's kind of a moot point because we ignored the first three, so the last one really doesn't matter in this example. Why do I think this is important? Because we're living in an era of high risks for people. Pandemics are an example. This pandemic's over, but the risks of pandemics remain. And with climate change, the climate change in the Colorado Basin is an existential threat to the big cities in the Southwest. And it's an existential threat because the science was ignored. So I'm not saying it, it'd be tempting. If I was a hamster, maybe I'd say, well, everyone needs to listen to hamsters, we know everything. It's not super credible. I'm not saying that scientists should be running the everything, but science needs to be included in policy making. And we have to find a way to do that, or things are not going to end well, for us as humanity with the way we're treating the planet. And I know an audience, by definition, you're showing up here. You're probably not the people I have to convince of any of this. But we need to make sure that science is included in policy making, and that is also true for the water. I think it's very simple why the water management went off the rails. But be that as it may, I hope I've taken you through sort of an interesting journey through this 100 years of these fantastic developments in cosmology, and given you maybe a little sense of wonder of what we can achieve when we apply the scientific ideas sensibly and rationally. There is an external universe out there. Not everything is a matter of opinion. We actually can discover things about objective reality, and I think that's something to keep in mind moving forward through this uncertain century that we're living in. So thanks for your attention, and thanks for coming. So I went on a bit long, but maybe I'll take a couple of questions if there are any. Yes, the gentleman in front.
Yes. What happened in the 3 minutes prior to the Big Bang? Why didn't the Big Bang happen 1 second earlier or later? What's the latest theory there?
I have no idea. Maybe some of my friends here know, and my colleagues, but I don't think we know the instant of the Big Bang what happened. We don't have the theory. I mean, my answer would be, well, we need quantum gravity, and I don't know, maybe Bernie or someone, but I don't think, some of my colleagues are there in the back row, but I don't think we have a theory of what happened before the Big Bang. What Martin Rees says, the first millionth of a second after, we're pretty good with our physics, but our physics sort of breaks down, and so we're sort of faced with a mystery there. So science doesn't explain everything, that's for sure. But a good question. I'm sorry I can't give you a better answer. Yes, and then...
Dr. Rhee, okay, not until 100 years ago did we realize there were galaxies out there.
Correct, yeah.
So, and then as technology got better, we found out there were, maybe thousands, then it went to millions. And when Hubble came, it was billions. Now with the new James Webb, it looks like it's going to go into the trillions. What do you think?
How many galaxies?
Yeah.
I'm not sure the James Webb is, well, yes, it is finding more galaxies, but it's not so much that it's looking further into the past. So it's not that we're surprised that there are even more galaxies than we thought. It's just we're looking further back into the past. So the galaxies nearby, I don't think the James Webb has increased the density of known galaxies. It's just revealing the history of the universe. It's looking further back in time.
Because that was the part of my question was, did you guys expect? Okay, so you don't think that the mass in the universe has increased because we're finding little galaxies?
No. The density estimates are unchanged, yeah. So it's more that we're pushing further back in time. So we're looking into the history of the universe, but not revealing new galaxies nearby. So far, I mean, the Webb just got started. It's been about 6 months. So stay tuned. I don't know. They might find some stuff. That's always exciting in astronomy when you look into a new regime where you haven't looked before. Usually the most surprising thing is something unexpected that you weren't looking for. So we may make discoveries along those lines. But for now, no, it's more the power of the Webb for cosmology is to look further, earlier into the universe, to really the cosmic dawn, to see the first stars switching on. I think there was a question here, yeah?
Yeah, a question actually related to the James Webb telescope. Is there a theoretical limit as to how far back in time the telescope can find galaxies? And say there's no theoretical limit and it could get back very close to the Big Bang. What would it say?
Well, there's a limit in the sense that, I didn't go into this detail, but the cosmic background radiation, in my 60-year-old analogy, if the universe is 60 years old, this cosmic background, if you remember the fossil that I talked about, we've managed to image it in great detail with NASA satellites. And it shows that there was a time in the universe when there were no galaxies. So we know that for a fact. It's much too smoothly distributed, that radiation. So we know that it's not infinitely back in time. There was a finite amount of time when the universe was about a few hours old, just to not bombard you with hundreds of thousands of years. if the universe is 60 years old, the cosmic background radiation is a picture of it when it was a few hours old. We know there was a time from observations when there were no galaxies and no stars. And with the Webb, we're trying to push further and further back to just see the stars can't have formed immediately after that picture of the cosmic background. It must have taken some time for matter to clump enough to form stars. And that's modeled by in computers. But now we're actually, for the first time, being able to push with observations. So we're dealing with a finite amount of time, and we know at one point in the universe early enough there wasn't anything, and we know as far back as we can see there is stuff, but at some point we must reach the edge where there were no stars and galaxies. And there's a lot of work underway to try and find that time, that transition time between what they call the dark ages, early in the universe where there was nothing, to when the first stars, the sort of genesis moment when things started to shine. I don't know if that makes any sense, but I hope it does. I don't know, I see hands. This gentleman in the back?
How do we give such a defined point of time of the state of the universe if the time in which the Big Bang occurred is different than the time we perceive on Earth? Because the time of the space-time curvature at that point in time is different than how we perceive time now.
I mean, naively, you can imagine, very roughly dating the universe, you can imagine if you see a galaxy a certain distance from you moving at a certain speed, then you can say, well, let's say I'm going at 60 miles an hour and I'm in St. George, 120 miles away, then when did I leave Vegas? Well, 2 hours ago. So that's kind of how they date the universe, roughly. Except the expansion has slowed down, or rather it's accelerating. It didn't go at constant speed, and we know that too. But that's roughly how we date the universe. So it's sort of a common sense idea of maybe measuring distances and measuring speeds and saying how long would it have taken, to get that far. I think that's a simple explanation of how we do that. So let's see, there's so many hands going up. Let's see the guys at the back, because I can't, yeah.
Could you repeat the books that you recommended?
Oh yeah, so one is, there's shelf loads of books, but I'll stick to two just so we can focus. One is called The First 3 Minutes by Steven Weinberg. And it's about precisely how we calculated the fossil, the prediction of the background radiation, and what happened, how hydrogen went into helium. I think it's a fantastic description that we can actually say anything, about what was happening in this room 14 billion years ago. That's the first one. The second one was Just 6 Numbers by Martin Rees. And so, you can knock yourself out with books. There's a lot of books out there that are amazing. But those are the two I would recommend, just to select two that highlight important aspects of this story, measuring these numbers in different ways to convince ourselves that we're measuring something real. Yeah, you, sir, and then you. Yeah.
Very specific. The eclipse and the position of the stars predicted by relativity versus Newtonian. What's the magnitude of that difference?
Oh, my friends would know better than me, but I think it's a factor of 2. The Newtonian thing is kind of a hybrid, just assuming light has mass and then the mass of the sun. So it's not, I would say, I don't think Newton really made a prediction, but I think, as I recall, it's a factor of 2. Einstein predicted twice as much displacement. And so with the telescopes of the time, it was a rather difficult measurement. But you can look it up. Actually, there's a book whose title escapes me where he talks about that.
I'm just being lazy.
Yeah. No. Yeah, it was a tricky measurement, and I think you can find the images on the internet if you look it up, and find the paper itself if you're curious. Yes, sir.
Some of your work, I guess, is with dark matter. Are there any theories about how the formation of dark matter, as far as fitting into the Big Bang?
There are, but I'm not familiar with them, unfortunately. In my work, or in the work of cosmology, they've assumed, well, a dark matter particle appears and it has these properties. If it has these properties, we can match the visible universe to our theories. There's a whole aspect of what we call large-scale structure of the universe that I didn't talk about, where the galaxies are sort of distributed on a web, and the properties of the dark matter. But it's basically an assumption as far as I'm concerned. Unfortunately, we have no evidence. So we assume if the dark matter has these properties, if it has this mass, if it was moving with this speed, etc., we can explain what we see. It would be very helpful. I'm kind of just stuck as a sort of pragmatic scientist. It would be helpful if we could detect it. I think that's, but it's a good question, but I just don't know the answer. I'll take one or two more, and then I know people want to probably walk around and stuff. Yes, sir, yeah.
The findings from the new James Webb telescope, does it strongly support the Big Bang theory?
Oh, yes, yeah. I mean, the Big Bang theory was controversial in the 1960s. There was a guy called Fred Hoyle in the United Kingdom who had his own steady state theory, but I think the evidence for the Big Bang, I don't think there's been any evidence conflicting with the Big Bang theory. I mean, we're open to evidence. That's been the whole theme of my story. If evidence comes, we're ready to say. The reason I'm skeptical is because it's so heavily anchored in data. There's so many high quality observations. But I'm prepared to be surprised. But I have not, in a nutshell, no. I haven't heard of anything coming out of the web that's a problem for the Big Bang. What happened with the opponents of the Big Bang is they kind of died, unfortunately, and there were a handful of them that were simply not willing to give up. To be honest, for me personally, it's been a puzzle because they were brilliant. Fred Hoyle was a brilliant man. He explained the relative abundances of the elements in the universe through the synthesis in stars. It was a puzzle to me how someone that intelligent could not change his mind in the face of that evidence. But I don't know, it was maybe his makeup, he was a stubborn guy. But that's a sort of question mark in my mind, how people that brilliant. I'll take one more. Oh, I got Bernie over there, yeah.
Yeah, just two comments. I'm surprised you didn't mention your own book.
Oh, that's nice of you.
Much more up to date. He didn't set me up for this.
Well,
And the other comment is, why didn't you mention Fred Hoyle in this whole story?
I just did. But yeah, I mean, well, Fred Hoyle was wrong on the Big Bang, and I think in terms of historical perspective, I've heard people say the controversy with Fred. He's talking about this guy who opposed the Big Bang, and it was viewed as more of a controversy in the UK between Hoyle and Martin Ryle, who were at loggerheads. My theory on Hoyle, I'll give it to you even though it's kind of useless, is, because I read his biography, if you're interested, it's called Home is Where the Wind Blows, and he was just an iconoclast by nature. He liked going against the grain. His dad was a machine gunner in World War I, and they told them to blast their machine gun at 10-minute intervals. And of course, if you do that, then the enemy can pinpoint where you are and blast you to smithereens. And so his dad survived the war by saying, screw that, I'm not going to do that, disobeyed orders, and survived. And maybe Hoyle was a northerner. For him, like for me, it was a long shot ending up in Cambridge. He felt like an outsider. I don't know, all these things pass into mystery, but I didn't emphasize it. I mean, I have an anecdote for all of these guys. I wrote to Hoyle when I was a kid, and when I was 16, and said, I want to be an astronomer, what do you think I should do? And he said, go anywhere but Cambridge. He was so enraged. And I ignored him, but it was cool. I wish I'd kept the letter. He was one of the great scientists of the 20th century. I got a job offer from Margaret Burbidge, who was on that paper. Luckily, I came here. It was a postdoc, but I look with disbelief at my life that I've encountered these amazing people. If I'd gone to work for her, I would have loved to hear from her husband, who was a friend of Hoyle's, who also dug in anti-Big Bang. They didn't budge as the evidence kept accumulating. I've never understood that. But who cares? It's just human nature. The real punchline is... But anyway, why I didn't mention Hoyle is more, I've heard it that it was a bigger brouhaha in England. There wasn't so much opposition to the Big Bang in America. But yeah, I could have mentioned him. And thanks for the book mention. I'm not trying not to sell anything, but to invite you here to enjoy science, which I enjoyed as a kid and inspired me to be a scientist. So that's why I didn't mention my own stuff. And
What's the name?
it's called Cosmic Dawn anyway, yeah. But thanks for coming. And I've got an email list here if you want to sign it. And it's great to see so many people here. Don't forget about the next lecture in February. You want to say a couple of words? Or?
Yeah.
Go ahead.
Just by way of wrap up, I wanted to thank everyone for being here this evening on behalf of the College of Sciences. My name is Kara Peterson. I'm the new Director of Development for the college. And we wanted to thank Professor Rhee for organizing this evening. And I think really honoring the intent and the vision of Russ and Brenda Frank in sharing continuing education. Many of you know Russ, that he has taken classes at UNLV in physics from in the graduate level courses just for the hell of it, for fun. And I think this honors that continuing education legacy that is the intent of this lecture series. As you mentioned, we have like the sign-in list, and then we also have ongoing trivia nights that are hosted by the College of Sciences. You can ask for the details about those kind of events. And just again, want to thank you for being here, and have a great evening.